Alright, this will be Conservation of Energy 3. This time we are going to deal with projectile motion. So we have the ground. Let's say we've got a spring we compressed some distance. We shoot. And let's say we're interested in max height. Let's say that's the question. Alright. This time we do have to deal a little bit with the idea of vectors. Because we know when this goes and the velocity is reached, and when it releases, and we've got a velocity vector going this way, we know that velocity vector has two components. We know it's going to have a v of x and a v of y. We know that. So we do have to take that into account when we talk about the overall scheme of things. So this is situation 1, this is situation 2 at maximum height. Now at maximum height, we know the y velocity is 0, but the x velocity is still there. Which means at the top of the projectile motion path, there is kinetic energy. Because there is an x component we have to take into account. So, when we do this, remember we're perfect world and air does not exist. So in this case, it's just energy initial equals energy final. In situation 1, that's our initial, which is our spring. So potential energy of the spring. At the top, it's reached maximum height, so that's gravitational potential energy. But remember, it's also moving forward. So you can put kinetic energy, and you can even put a subscript x to remind you that it is still moving in the x-axis. You cannot forget about that little detail. So here are some options of how to deal with this little problem. So we know this is true for phase 2. However, here's the issue. We need v of x. So why don't we start at position 3, the moment it's released. So this is 1 to 2. Let's do 1 to 3. When it goes from here to there, all that energy from the spring is going to be converted into kinetic. So let's start there first. Spring initial equals kinetic energy final. Let's see how fast that thing's moving once it's released. So we're at position 3. So 1/2 mass, 1/2 spring constant. Displacement squared equals 1/2 mass velocity at 0.3 squared. What you need to solve for is that velocity. Once you know this velocity, then you know that's the maximum velocity can ever go, right? That's the one we need, because the x component of velocity is buried in there. Which means we now can use our trig and go x component equals v3 cos theta. That's what we need. This value here will be what we put in to the kinetic energy equation there. Because the rules are, if there's no air, then the x component of velocity is the same at all times. So let's go back and see how we dealt with this. We have a spring that's compressed or a slingshot that we pull. That potential energy is released, converts all to kinetic, which means we have a velocity. This velocity is a vector, which means there's a y component and an x component. And we know in our projectile motion that air does not exist and that the x component of velocity will always be a constant. At this point up here, it is still moving in the x-axis, so that kinetic energy must be kept. The key is, what velocity do we use? We only use the x component of velocity at max. That is how we deal with projectile motion problems. All movements are taken into account, but they're taken into account all in the same equation. So this, in a lot of ways, is much easier to do than your projectile motion, other projectile motion way, using kinematics. You could actually go back to a lot of your kinematics stuff and solve them this way. That might actually be a good exercise.